Hi, welcome to another lecture on Calculus 3. Today we are going to continue our lecture on tangent planes and normal lines. We are going to do two more application problems. Let's go ahead and take a look at this. So in the last lecture we did problem 1 and 2. Today we are hoping to do problem 3 and 4. Problem 3 is equation of tangent line to the intersection of two surfaces. So we have two surfaces in space, they cut each other on a curve. We want to analyze that curve. Many questions can be raised about that intersection. For example, what does it look like? What is the tangent line to it, and so on. Question number 4 here is inclination angle of a tangent plane to a surface. So once we have a tangent plane, sometimes the question comes up what angle it makes with the xy coordinate plane. This is very similar to the question that is raised in Calculus 1. Over there, equivalent problem would be you have some curve, you draw the tangent line to it, and then you want to know what angle it makes with the x-axis. Now we have the same question in 3D. We have a surface, we draw a tangent plane to it, and the question is what angle it makes with the xy coordinate plane. Let's go ahead and take a look at these two. So for question number 1, equation of tangent line to the curve that's at the intersection of two surfaces. Let's see what so you remember the main ingredient in all these problems is gradient. That's a generalization of the notion of slope. So last time we mentioned if a surface is given to us, so here's a surface, we bring everything to one side, take the partials, and that makes a vector for us. That vector is perpendicular to the surface. Now what we want to go to do with that vector is going to be different in all these 6 problems, and for today we are going to have another application of gradient. So here's a question from your textbook. Consider two surfaces, one of them x squared plus z squared is equal to 25, and the other one is y squared plus z squared equal to 25. Question is find the equation of the tangent line. Find equation of tangent line to the curve of intersection of these surfaces. They cut each other on some curve, and the question is focus on point coordinates 3, 3, 4, and then find out what that line is going to look like. Okay, the two surfaces that we have are very basic surfaces, so it would be easy to visualize them. Again, let's pause for a second. At the very beginning of the semester we talked about these simple surfaces. Let me see if you remember what each of them is, and you try your hand at answering the question, perhaps finding some handle on it, like what does the intersection look like, and so on. So again, pause and do as much of it as you can and then come back. So well, what is x squared plus z squared equal to 25? If we were just in the xz coordinate plane, well, that would be the equation of a circle of radius 5. And since y is missing, we remember from beginning of semester, when y is missing, we are dealing with this cylinder. This is a cylinder whose axis is in the y direction and has a radius of 5. And this other one, y squared plus z squared, that's another cylinder. The axis of this one is x-axis, and the radius of this one is, fortunately, 5 again. So we have two cylinders with two axes, one x, one y, and they are intersecting each other. What does the whole thing look like? Again, I invite you to try to visualize it, to graph it for yourself. And since pretty much all of you are engineers, you actually should know some very basic tools or housing pieces related to plumbing that look like this situation here. Let me see if I can convince you by, so again, you try to do it yourself and then we come back here. So two cylinders with their axes perpendicular to each other. So these are the two cylinders. Let me make the picture less crowded. Okay, two cylinders are cutting each other, so this is what you imagine the situation is going to look like. Of course, the thing that you see in the plumbing section of a hardware store, here is open, and you have a way of connecting two plumbing lines. What we are interested in is what's happening at this intersection. You see this intersection here, this curve. We want to analyze that. So you can ask, for example, what's that shape? Various other properties. A simple question that can be asked is, well, what is the tangent line to this curve? That's a question we can easily answer by using gradient. So what is it that we are after here? So let's here I'm coloring the intersection. You see this rainbow color, that's where the intersection is sitting at. It happens to be an ellipse, and as we go on it, we can ask what's the tangent line to it. So here's a vector that's in direction of that tangent. As you go around, you can see that that vector tries to come along with you. That's what we are after. Describe that tangent line. So we know what's happening at the intersection of these two cylinders. Let's go back and see how we do that. So that's problem 1 for today. That's in our original list. Problem number 3. So to do that, I'll need to take you back to some basic steps from Calculus 2. Probably you have seen it in Calculus 2, and then you have seen it in the physics, in the engineering classes. All of them cover the same topics related to cross product of two vectors. So for the lecture to make sense, I go and do a quick review of a cross product and its properties and so on. We are going to be quick, so you have to go back to some other lectures somewhere else perhaps to get more detail. So if I have suppose I have well, let me draw this thing better than this. Here's a plane, and I have a vector here. Let's call this say vector n1, and then another vector here. Let's call it vector n2. What we want to do is to make sense of what it means to cross multiply these two vectors. So okay, that can be an extensive lecture by itself. We were just doing a quick review, and let's see. Uh, the cross product of two vectors is a vector. First of all, this is a vector. Okay, let's call it L. We want to describe what L looks like. Here's property number one. L is perpendicular to the plane that contain these two, perpendicular to both of these things. So it's going to look something like this. So this is L. L is perpendicular to both n1 and n2, and therefore to the plane. Let's call this thing the plane. What's a good name for a plane? Plane pi is perpendicular to all three of these things. Second, how long is this vector? We don't need that for the problem that we have at hand, but just to have a complete description, something good to know. The size of this L is equal to the area of the parallelogram that you can build with these two vectors. So that is one way to describe that is n1 times n2 times the sine of the angle between these two vectors, and that's also area of the parallelogram you can build on n1 and n2. Okay, so first it's perpendicular, second is the size, numerically is the size of that parallelogram, area of the parallelogram, and third is the so-called direction. Each vector has a direction. Should I go up or down? And this is something that in your engineering classes or sometimes calculus classes they refer to the right hand rule. They say take your four fingers in direction of n1, rotate it toward n2. That would be your right hand. So your right hand, four fingers in direction of n1, you rotate it toward n2. The direction of your thumb will be in direction of L. So L is determined by direction of L. It determined by right hand rule. Okay, the only item that is relevant to us is the fact that to get a vector perpendicular to two other vector, cross product will do it. Okay, after all of this, well, how do you actually do it? I mean, how do you calculate it? This is a physical description of it. How do you actually figure it out? So the way we figure it out is, let's suppose n1 is a vector with three components, a1, b1, c1, and n2 is another vector with components a2, b2, c2. Then n1 cross n2 is the determinant of a matrix whose first row is I, J, K. Second row is the numbers A1, B1, C1. And the third row is A2, B2, C2. Well, now we kind of jumped from the frying pan into the fire. Do we remember how to do the determinant? So again, I'm going to be doing just a shortcut for doing this. Issue of determinant by itself can take a couple of weeks of lectures as to what it is. We just do the very basic case here. Best thing to do is do an example. So here let me do something with numbers, and then that will give you an idea. Suppose A1, B1, C1 was say 1, 2, 3, and this one was 4, 3, and well, let's put different numbers so that they don't collide with each other. So 4, 5, and well, say -1. How do you find the determinant of this? The way to find the determinant, one easy way, is to duplicate your matrix. So at least the first two columns of it, 4, 5, -1. So I duplicated my matrix. Okay, remember I, J, K are vectors. These are the unit vectors. We have seen them from beginning of semester. Now what we do is that we are going to take diagonals. So you see I have this diagonal, and this diagonal. So 3 diagonals going right. I'll be multiplying each of them with the +1, and 3 diagonals going the other way. So here's 3 diagonals, 1, 2, and 3. I'm going to multiply these things with -1 and add up all the 6 pieces. So it's kind of a jungle, but it can be done easily, patiently, and you're done. Your other teachers might have described this in a variety of other ways. Sometimes even as far back as high school, they go through determinants and give shortcuts for calculating it. Just remember, a determinant is a monster, and there is really no shortcut to it. While we offer these kind of rather gimmicky style of calculating them, that applies to 2 by 2 or 3 by 3. The issue can be quite complicated. So just take this with a grain of salt as to this is how we calculate it. And there isn't much substance to this style. For example, if you have a 4 by 4 matrix and you want to calculate its determinant, it's substantially more complicated. It doesn't, these diagonals wouldn't cut it. You have to do other things. Okay, so you are going to study that in linear algebra. Let's go ahead and do it, what the minimum we need for here. So I'm going to multiply I, 2, and -1, so that's going to be -2i. J, 3 and 4, that's going to be 12j. K, 1 and 5, that's going to be 5k. And then these green lines we have to also multiply by minus, so it becomes -i, 3, 5, so that's going to be -15i. This one is going to become what? 1 -1, another -1, so it becomes a +j, plus 1j, just to remember. And this one is going to be -8k. Okay, you just clean it up. -17i plus 13j minus 3k. So if you want to simplify this, how would you write it? In short, what we had is 1, 2, 3, vector 1, 2, 3, cross with 4, 5, -1 is the vector. That's what we get here. -17, 13, -3. If you want to write them with ijk's, 1i, 2j, 3k, cross with 4i, 5j, -1k. They would write this thing as just -k. -17i plus 13j minus 3k. Okay, hopefully I haven't made an arithmetic mistake. Let's just double check. 2 minus 2 plus 12 plus 5 minus 15 plus 1 minus 8, and we should be good to go. So that is the cross product of two vectors. Well, why do you see this thing in physics? Well, the thing is all over the place. Calculating torque, you have a force vector times the arm vector, and that gives you the torque. Like for example, when you're holding a steering wheel and you apply some force to it, and there is a force, and then there is the arm. You have to cross the two of them, and it's a standard issue in variety of things in electrical engineering and so on. So it's a very basic thing. Okay, issue number one, we did a quick review of cross product. Now, with respect to these properties, that this vector is perpendicular to both of these things. How do we know that? How do we know that something is perpendicular to something else? Well, the easy way of doing that is to check with respect to dot product. So let's consider this one N1, this is N2, and this is L. We are saying that L is perpendicular to N1. How do you know that? How do you check that? So L is minus 17, 13, minus 3. You want to check that it's perpendicular to somebody else. It's 1, 2, 3. What should be the dot product of two vectors that are claimed to be perpendicular to each other? Quick question. So let's pause for a second. What is the dot product of two vectors that are supposed to be perpendicular to each other? It's supposed to be 0. Let's see if I've made a mistake or not. Is it 0? Well, how do you do that? First times first, minus 17 times 1, second times second, third times third. That's minus 17 plus 26 minus 9, and what is that? It better be 0. Well, lucky for me, it is actually 0. So L is perpendicular to N1. Is L perpendicular to N2? You go ahead and check the same way to see that it is perpendicular. Let's do that quickly. So it's a 4 times 17 plus 5 times, minus 17, 5 times 13, minus 1 times minus 3. What is that one? So this is going to be what? Minus 68 plus 65 plus 3, and bingo, that is also 0. So our claim is that when you do a cross product, the result is perpendicular to the vectors that you have. That's the main ingredient what you need. You go ahead and check that the areas or the length matches the property that we set here, and so on. Okay, now what are we going to do with this thing? What about it that you do a cross product? What does that have to do with finding this thing? How does cross product connect to the property of this curve? We were finding a tangent line to this curve, this purple line that you see here. Let me rotate the picture that you see, for example. See that arrow? That arrow is going in the direction of this curve, is tangent to that curve, and that is what we are after. So let's go back and see how do we do actually. Let me stop this thing. Okay. Well, graphically it's easy to visualize it and figure it out, but how do you calculate it? Okay. Review item number 2. Suppose I have a plane and then I have another plane. These are going to be our actual tangent planes. If you have two planes and they are intersecting each other, how do I find the line of intersection? So the question is how to find line of intersection of two planes. Well, why am I reviewing this thing? We are taking the problem to its simplest level. They have given us a problem that looks quite hard, which is I have two surfaces, they intersect each other, and I want to find the tangent line to the curve of intersection. When we are facing a big problem like that, first we go after the easiest thing we can actually solve. Well, if the two surfaces were flat planes, the ordinary planes, then their intersection would have been a line, and the tangent line to that line would be just that line. So here's solving the problem at the simplest possible level. If I have two planes, how do I find their intersection? So again, going back to things that you might have seen in either Calculus 2 or your physics or engineering classes. If I have this plane, what does that mean? It means I have access to the information as to where is its normal, and I have access to normal of this one. I know the normal of this one. If I know the plane, I better know what is the normal to this and normal to that. Well, what is this intersection? Well, if I draw the n1 and n2 here, you see that the intersection line is actually a cross product of, so this thing is in direction of n1 cross n2. Why? Because n2 is perpendicular to this blue line, n1 is perpendicular to this line, so this is a line that's perpendicular to both n1 and n2. That's exactly what we talked about here. This is a line that is perpendicular to both of these two vectors. So to get the direction, all we have to do is to cross the two vectors. Once I have that, then I know where the crossing line is going to be. Okay, so we are all ready to go now. So what we do is write the two surfaces. So surface number 1 was x squared plus z squared is equal to 25 or something like that. For surface number 2 was y squared plus z squared equal to 25, like that. So we said standard procedure, bring everything to one side, even though in this problem might not need it, but just to follow standard. This is surface 1 is f equal to 0. Surface 2 is another function. Let's call it y squared plus z squared minus 25. So this is f equal to 0 and this is g equal to 0 are these two. We just learned that the perpendicular to these are given by their gradient. So gradient of f, what's gradient of f? Differentiate with respect to x, well that's 2x. Differentiate with respect to y, well luckily there's no y here, so this becomes a bit simple. Differentiate with respect to z, well that's just 2z. What is perpendicular to the surface number 2? Well, take the gradient, you will know. So who is this? This is our n1. Who is this one? That's our n2. So we are preparing the groundwork. With respect to x, nothing. With respect to y, it's 2y. With respect to z, that's just 2z. Okay, do everything at a certain point. At p0, p0 was given to us. What was the number? Let's see, 334, I believe it was, wasn't it? Yes. We are always at the big given some point at which we are operating. So p0 was 0.334. So the two vectors right now they are just given with some variables, but when we calculate it, x is 3, z is 4, same point, so 0, and then this is 6, and oh excuse me, this is 8, this is 8, we're doubling them. So n1 is n2 is this one. Next we have to figure out what is n1 cross n2. Well, that's going to be, we said you write ijk, you write the first vector, who is first, who's second. In this case it doesn't matter however you do it. If you flip the order, instead of going from, let's say, left to right, you'll be going from right to left. You're flipping the direction of the line, but that is still that line. So okay, so how did we say we do this? We said we patiently ijk 608 068 duplicated by duplicated IJK 608068, and then we are gonna go, luckily this is 0, luckily this is 0 again, and then I have this one, well, that is 36K. Now going the other way, this one is, what is that? Yeah, I forgot my multiplication. So you have to multiply by -1, so minus 48 I, and again minus 48 minus 48J, and then this is double 0. So that is going to be the vector that's the cross product of these two. So I can write it nicer. So minus 48 I minus 48J plus 36K. This is the direction of that line that is tangent to the intersection of these two cylinders. Okay, the line that is tangent to both of them is in this direction. If you want to make it simpler to yourself, you can, for example, divide this thing by their common factor. For example, you can factor a 12 out of it, make your numbers a little bit more reasonable, like 12 minus 4J plus 3K. Then you can talk about this as the direction. Smaller numbers are more understandable as to what's happening. Okay, that is in the direction of the line. What's the equation of the line itself? Equation of the line, through a point, let's call it point P0, in direction of a vector, in this case vector L, is, what is that? The location you're after. Start from where you want to start, plus in a multiple of the direction you're supposed to travel on. Okay, equation of a line. This is advanced style of writing equation of a line, a bit better than what you see in college algebra and such. So in college algebra, equation of a line, you had y equal to mx plus b and stuff like that. When we come to okay, so what do you have there? Let me just compare it. You have y is equal to b plus you have x times m. Is that right? Y equal to I wrote it like this so that you can compare. This is essentially the same thing. This is like a starting point. This is indication of the slope that you are going, and this is the multiple of that slope that rise that you're taking up. So in a higher dimension, P, instead of just being a y, is x, y, and z, all of them. Instead of B, that's your y-intercept, in this case it's just some starting point. Our starting point was what? Our starting point was 3, 3, 4. Instead of x, we write a multiple t. So L, it's your choice. These big numbers, if you're comfortable with that, or if you factor anything, that would be even better, easier to handle, easier to see. Minus 4, and 3. That's the equation of line. Now, we said, so this is called parametric equation or vector equation, sometimes called vector equation of the line. Different styles of writing it. One is the parametric form. Right, the first is equal to first plus t times minus 4y. First is 3, again minus 4t. Z, start at 4, its multiple is a 3, So it looks like three of those things you had in your algebra 1, y equal to mx plus b. Now we have both, all x, y, z, all of them with some factor of t in them. This style is called the parametric form. And then we said there is another style, they call it a symmetric form. You calculate t from all of these things, and then so what do we have here is x minus 3 over minus 4 is t. So is this one, y minus 3 over minus 4 is t, and z minus 4 over 3 is t. So what is the style of this? We write x minus 3 over minus 4, and the y minus 3 over minus 4, and the z minus 4 over 3. Symmetric form of the equation of the line is the following. So if you enter that into WebAssign, you might write it like this, or they might here's if you are entering this one, let's they might write it like this: x, y, z is equal, then inside of that big box that they give you to fill up, they sometimes might put these things for you, and then you say 3 minus 4t, first one, then comma, it tells you comma separated list of equation, 4 plus 3t. So that's how you enter it over there. Okay, so what did we do? Equation of tangent line to the intersection of two surfaces. We spent all this time to explain what was behind it and find this tangent to this intersection curve. That's what we did all this time. Now let's go to see how much time we have. This took a while. Tangent plane to inclination angle. Now let's go after number 4. This took longer than I thought it should take, but we did a review, so the review took half our time. And okay, so next question up, issue of inclination angle. Okay, so we said you have something like this in calculus 1. It's just called the angle. So if you have a curve at that some point on the curve, you draw the tangent line to it, and then this would be the angle that the tangent line makes with the horizontal. What we are after now is that what if we were in a higher dimension, say, so suppose we have a surface here, and at some point on the surface we draw a tangent plane. Okay, the question is, what is the angle between this tangent plane and the xy? What's the angle between, so let's call this tangent plane pi, and then we have this xy plane here. So the question is, what is the angle between tangent plane and any of the coordinate planes? Let's say and a coordinate plane typically Okay, as usual, we do a bit of a review to make the whole thing a bit more understandable than just giving a formula and say, okay, plug it here. So, if you are back in elementary geometry, suppose you have two uh, uh, two lines and you want to find the angle between the two of them. Okay, first observation is that that angle is same as the angle between the normals between these two. So if I draw a line perpendicular to one and perpendicular to the other one, these two make the same angle. Why would I make my life hard by going after perpendicular? Well, because we said gradient is perpendicular to the surface, and gradient is easy to calculate, so gradient is what comes to your hand first. And if you can find the angle between two gradient vectors, then you have the angle between the two vectors. So what we are going to do next is remind ourselves of another basic formula from calculus 2 or physics or engineering, is that if I have a vector A and I have another vector B, what's the connection between the angle in these two vectors? Well, the connection comes through the dot product formula. The dot of the two vectors is, we said, is equal to the product of the length of these two and the cosine of the angle between the two of them. So cosine of the angle is going to be the dot divided by the length of these two vectors. And if you want the angle itself, well, that's going to be arc cosine or cosine inverse of all of this. Okay, that's the end of our review. So next issue is, well, how do we use it? In this case, if you have a tangent plane, the normal to tangent plane to a surface given by some formula like this is, we said, gradient of f calculated at the point of interest. Now if you have another surface, in this case normal to the xy plane, if you have another surface, well, you go ahead and find the normal to that. In this case, well, normal to xy plane, you don't need to really work to get that. It's the vector k, or if you wish, 0, 0, 1. If you are in xy z coordinate plane, what's the description of this vector k? Well, that's a unit normal to xy. Its components are 0, 0, 1, and that's, so what we want is the angle between these two. Okay, so if you are looking for an angle, and that angle is the same as the angle between the two normals, and the two normals are given by the gradient and k, then the cosine of the angle that we are after is going to be k dotted with gradient of f divided by length of k times length of gradient of f. Well, since k is a unit normal vector, the problem becomes a tad bit simpler. It becomes k times gradient of f divided by the length of gradient of f. And of course, if you want the angle itself, is going to be arc cosine of k gradient of f over gradient of f. So let's go do a quick example. Here is find inclination of tangent plane to this one is, say, 2xy minus z cubed is equal to 0 at, now it's a nice point, 2, 2, 2. So that's my P0. So what do? First of all, I write my F. If they were on two separate sides of equality, I bring all of them to one side. In this case, well, there's nothing to do, so F is just that. Then take my partials, Fx, that's 2y. Fy, what's Fy? Quick, what's Fy? That's going to be 2x. What's Fz? Fz minus 3z squared. Is that right? At the point of interest, Fx becomes 4, Fy becomes 4, Fz becomes what? That's going to be minus 12. Is that right? Now theta is going to be the arc cosine of, remember, k 0, 0, 1, gradient 4, 4 minus 12 divided by the length of 4, 4 minus 12. As simple as that. So this becomes arc cosine of. In the numerator, it's very easy. When you multiply, it's just Fz minus 12 divided by, well, what's the length of this one? That's going to be 16 and 144. So our cosine becomes minus 12 over, I have 144 and 32 is 176. You can simplify it a bit, but in general, no. Okay, theta becomes this angle. Now it's customary that if the angles are given to be as acute angles, so the arc cosine of this quantity, so here when you use it, when you use your calculator to figure out what this arc cosine is, you get an angle that's an obtuse angle. By convention, if it is so, then we convert it to an acute angle. Like if I were to ask you what's the angle between these two lines, well, you have two choices. You can say, well, the angle is this one or the angle is that one. Yeah, both of them are legitimate way of looking at this. In case we get into an obtuse angle, the convention in your textbook is to force it to become an acute angle, and the way you do that is to add the pi to what you get from your calculator. Remember, pi minus arc cosine of, you subtract, of course, pi minus arc cosine of minus 12 over radical 176. So that's the step you take. If this is negative, your angle is going to be obtuse, and then you have to correct for that to get an acute angle. So that is just the basic convention. Okay, this became lengthy, but so we have done 4 just solving problems, and they're taking quite a bit of time. So let's put problem 5 and 6 for a separate lecture. Good luck and God bless.